All right, so let's get going on today's class. So, last time in Chapter 6, we introduced the final portion of the hypothesis test, the figuring out of the comparison distribution. So now we are ready to tackle our next type of hypothesis test, specifically the t-test, and that's what we're going to be introducing here today as we take on Chapter 8. So before we begin this, just want to let you know that this is the same hypothesis test. There's going to be a few little tweaks, but the same idea remains, the same 5 steps remain, and basically the same procedure remains, just with a little tweak to make sure that we're doing this as accurately as possible. So there's 2 types of t-tests that we're going to be taking a look at, single sample and dependent means. Today we're going to start off with the single sample t-test as a way of introducing the idea of this slightly new hypothesis test. Now before we get to that, typically I would normally be taking up the exam a week after we completed it. We still have, there have been some issues with the makeup exams, so we're going to be doing that hopefully next class. But just as a sort of check-in with all of you and to provide you with a little bit motivation as we enter our second half of the semester. If you recall, we previously saw the grade distribution, frequency distribution for exam number 1. So here we have the frequency of students attaining certain scores. Here we have the possible scores on exam number 1 all the way up to that perfect score of 100. And we saw that that was the performance of the class on exam number 1. And very satisfyingly, that is the performance on exam number 2. So you can see that the number of students that are struggling, that were not able to attain higher grades, they have now shifted up towards the 80s, the 90s, and the 100s. So we can definitely see progressions as we keep improving and keep developing our skills and keep honing those strategies and skills that we've been looking at. So keep up the work, keep going with it. We got 2 more exams coming up. We got a lot of hypothesis tests still to do, but I'm very pleased with the progress, and hopefully we'll continue to improve, and we can get everybody into those 80s, 90s, and perfect scores. All right, so today we are going to once again revisit Harlow and his monkeys, his infant attachment experiment. But this time we are going to do it in the most realistic way possible. So this time we're not going to make any assumptions like we know the distribution of the population distribution for how long monkeys spend with their terry cloth mother. We're going to basically recreate the situation that Harlow was in exactly and see the honest to goodness real life hypothesis test, in this case the t-test, that he used in order to determine that monkeys spent more time with the terry cloth mother than with the wire mesh mother, indicating that for monkeys, and then by generalization humans as well, have more of a need, more of a psychological need for closeness and comfort than was previously thought. So we're going to first do a little bit of foreshadowing, a little message from your future self, and then we're going to review hypothesis testing one more time, introduce the T statistic, which is an alternative to the Z statistic, and then we're going to do some hypothesis testing with the T statistic. So we are now getting to the point in this course where the mathematics required in order to do these hypothesis tests is getting to the point where it is going to be quite extensive. It is going to be quite involved. It's basically going to become very tedious to do by hand or using Excel. So the time has come where we can no longer, the types of calculations we need to do are no longer going to be easily done using Excel. So we're going to need specialized tools after today in order to tackle the rest of these hypothesis tests that we want to do. And the specialized tool that we're going to use is going to be SPSS. So next time we meet on Tuesday, we are going to introduce SPSS, which is a specialized program specifically for running statistical analyses. And we are going to basically recruit the robots to do all the sort of heavy lifting for us, all the sort of mathematical steps for us. And our attention is going to shift away from doing the calculations to, number one, putting the data, number one, analyzing and determining which hypothesis test should be done, formatting the data in a way that the machines will be able to understand it and know what they're looking at. And then after running the hypothesis test, interpreting that data in a meaningful way so that we can make a conclusion on our hypothesis test. So that's what we're going to be moving towards. So two things about that. Number one, this is going to be your last sort of peek behind the curtain in terms of the actual formulas and mathematics that are going on behind the hypothesis test. Number two is that next class, we are going to start with SPSS. And I'm going to assume that everybody has no experience whatsoever with SPSS next class. So we're going to talk about things in terms of how to open SPSS, how to access files in SPSS, how to enter data into SPSS. After that class, though, we're going to start moving more quickly with SPSS. Bottom line, if you ever needed to come to a class, next class is the one. So move heaven and earth, do whatever you need to do. If you are planning on maybe, not attending that day, or if something comes up, don't let it interfere. Come that day. Make sure that you are that you attend that class, because that's where we're going to be introducing SPSS, and then from then on we're going to be running with SPSS. So if you miss that class, you're going to paint yourself into a corner, and you're going to need a lot of catch up to make up the stuff that you missed. So again, next class we will be introducing SPSS. This class, however, we're going to do our final analysis using Excel and hand calculations. So previously on hypothesis testing, we were dealing with a situation where we had a known population. This is a very straightforward situation for teaching hypothesis tests, but honestly, in psychology, this is a very rare situation. So you very rarely know the mean of the population that you're working with, and you very rarely know the standard deviation of the population that you're working with. And what that means is that when we're figuring out our distribution of sample means from that known population, we're going to run into a problem, because if we don't know the mean and the standard deviation of the known population, we're not going to be able to determine the distribution of sample means, our comparison distribution from that known population. So again, what we did in hypothesis tests is we had this distribution of sample means from the known population that we figured out. That's our comparison distribution. And we took our treated sample and we figured out what is the probability that the mean from our treated sample came from this distribution of sample means. So what is the probability that it belongs to that distribution of sample means? And we analyze that by splitting up our distribution into a body and, in this case, tails for a two-tailed hypothesis. And if our sample was located in the body of the distribution, then we would say, or we would conclude, that that was a highly likely sample, that this sample likely belongs to this distribution of sample means, which means that it likely consists of people that came from this known population, and we would say that our treatment has done nothing because it hasn't changed this population. On the other hand, if our treated sample ended up in the tails, then it is highly unlikely. It is very, a low probability that it came from this population, because there's very few samples in those tails, which means that it's unlikely to still belong to this known population, which means that our treatment did something. So as I mentioned before, we were able to do this because we had a known population. And if you have a known population with a known mean and a known standard deviation, you can figure out the distribution of sample means and what the mean and standard deviation of that distribution is, which means that you can figure out your z-score and you can find out where your sample is on this distribution of comparison means. However, today we are going to get into a more realistic situation where you're dealing with not a known population, but an unknown population. And we're going to start with the situation where the mean of your unknown population is what's known as hypothesized, but the standard deviation is unknown. So we'll talk a little bit more about how you can have a hypothesized mean. But basically, it boils down to the idea that if you're dealing with a fixed quantity of something, and you're dealing with a known number of categories, you can hypothesize a mean. So, for example, if there are 24 hours in the day, and you have two locations that you can spend your time in, you can either go to IUSB or you can stay at home. I have no idea what the mean time that students spend at IUSB is. I have no idea what the mean time that students spend at home is. But if these are the only two places where students are, and they have 24 hours in a day to spend in one of those two places, then I know that if our population was a population of students that had no preference between staying at IUSB versus staying at home, I know that that population would spend half of their time at IUSB and half of their time at home. So if there was no preference, i.e. the null hypothesis, between spending time at home versus spending time at school, then I would have a hypothesized mean where 12 hours is spent at IUSB, 12 hours are spent at home. So that's one example of how you can come up with a hypothesized mean. And that's what we're going to be dealing with first. So we have a hypothesized mean. We know what should happen if the null hypothesis is true. But notice we know nothing about the spread. We don't know anything about the standard deviation. Maybe it's a tight population distribution. Maybe it's a really wide population distribution. We don't know. Importantly, what that means is that when we do our distribution of sample means from this unknown population, we're missing some information. Because while we still have the mean of the population, remember we have that hypothesized mean, we're missing this piece. We don't have that standard deviation. And if we don't have the standard deviation, we cannot figure out our distribution of sample means. And if we can't figure out our distribution of sample means, then we can't find out where our sample is. We can't calculate a z-score for our sample. And if we can't calculate a z-score for our sample, we can't do a hypothesis test. So we're in a position right now where we are unable to calculate this distribution of sample means and carry on with our hypothesis test because we have an unknown unknown variability, unknown variance for our unknown population. So what are we going to do in order to fix this very common type of situation in psychology? Well, we're going to introduce a new statistic. So we can't do the z-statistic. That's gone. We can't do that anymore. So we're going to introduce what's known as the T statistic. And this is the alternative to the z-statistic. So for an unknown population, in this first example, we have a hypothesized mean. So a mean that would occur if our null hypothesis was true. We have an unknown standard deviation. We don't know how wide it is, right? We don't know if every student would spend 12 hours at IUSB or if there would be a wide variability in how many hours people spent at IUSB to just average to 12. We have no idea how spread out this population is, so we cannot calculate those parameters for the distribution of sample means. We can't use that central limit theorem to figure out what the standard deviation is of our distribution of sample means. So because of that, as I mentioned, we need to change a little bit, and we need to introduce the T statistic, which is an alternative to the Z statistic. So just to put any worries you might have to rest, most of this is not going to change at all. And the stuff that does change is going to change a little bit. So for example, out of our 5-step hypothesis testing procedure, step number 1, restating the question as a research hypothesis and a null hypothesis about the population. That's not going to change. So everything you learned before, keep doing it. It's the exact same thing. Restating the question as a research and null hypothesis has not changed. Determining the characteristics of the comparison distribution. This actually does change. All right, so this is going to be what we're going to be working on today. This is going to be the major difference. Determine the cutoff sample score on the comparison distribution in which the null hypothesis should be rejected. This will also change. All right, so we're changing the comparison distribution. We're going to change how we find that cutoff sample scores, those lines in the sand. And then step 4, determine your sample score on the comparison distribution. So take our sample's mean and find out where it is on our comparison distribution. This is going to have a very slight change. So this is kind of a blink and you'll miss it change. I'll highlight it, but really it's going to be the same old thing that we were doing with z-scores. And then finally, for step 5, deciding whether or not to reject the null hypothesis. That does not change whatsoever at all. So we have step 1 and step 5, no change whatsoever. Step 2 and 3 is going to change. Step 4, barely any change. So let's start taking a look at what has changed. Let's start with step number 2. Determine the characteristics of the comparison distribution. All right. So you'll notice that we do not know what the spread is of our unknown population. However, we happen to have a sample that came from that unknown population. And as you've seen before, we can use sample statistics to estimate population parameters. So that's going to be the basic difference between what we did before and what we did now, is that instead of taking the population standard deviation, which we can no longer take because it's unknown, we're going to take the sample's standard deviation and we're going to use that to stand in for the population standard deviation. So we're going to estimate that unknown population variability using our sample's variability. And that is the basic difference. We don't know what the population variability is. We're looking at a sample and we say, hey, we'll use this sample variability and that'll stand in for the population variability. So recall that population variance was equal to the sum of squared deviations divided by the size of your population. Population standard deviation was equal to the square root of the population variance. So we don't know those numbers. We're going to use our sample variance to estimate those. And sample variance is the sum of squared deviations divided by the size of your sample minus 1. That is known as the sum of squared deviations divided by your degrees of freedom. So we're going to hear a lot about degrees of freedom, and we're going to see that most of the time degrees of freedom are, in this case for samples, the size of your sample minus 1. So what do we mean by degrees of freedom? Why is it always, in the case of a sample, the sample size minus 1? Well, there's a technical reason, and then there's an easier way to understand it. I'm going to try to give you the easier way. We're going to go to a barbecue. All right. Let's say that you go into a barbecue, and there are 5 meals left at this barbecue, right? So there's 5 things that you can choose from, and there's hamburgers. There's hamburger. There's 1 hamburger left. There's 1 hot dog left. Somebody brought some pizza. Somebody brought some corn. And then somebody brought bland potato salad with unnecessary ingredients like raisins. All right. So, 5 things, right? 5 things that people can eat. How many degrees of freedom will there be? I.e., how many people going to this barbecue will have a choice? So you have 5 things to eat. You can feed 5 people. First person comes along. They're taking a look at their selections. They have a choice. They have a degree of freedom. So they walk up there and they say to themselves, all right, barbecue time, hamburger, that's what I love. So I'm going to take the hamburger. I choose to take the hamburger. I have freedom to take the hamburger. 1 degree of freedom. Next person comes along and they say, you know what, I'm going to make a choice as well. Seems a little unorthodox, but I'm going to choose a pizza. 2 people had freedom to choose, 2 degrees of freedom. Third person comes along. And they say, all right, hot dog, corn, bland potato salad with raisins. I love myself some corn. I'm going to take some corn on the cob. 3 people have come along, have had a choice, 3 degrees of freedom. 4th person comes along. 4th person says, all right, hot dog or bland potato salad. I want Karen's potato salad, so I'm going to take hot dog over here. 4th person had a choice. 4 people had degrees of freedom. The 5th person will get fed, but that 5th person has no degrees of freedom. That 5th person is eating potato salad. So in a sample of 5 individuals, 4 people had degrees of freedom, 1 person did not. And that's where that n-1 comes from. Because in a sample, 4, in this case, if a sample size was 5, 4 of those have degrees of freedom. 1 person in the sample does not. So that's why we have those degrees of freedom, and that's where we're calculating. That's why that correction works when we're calculating that sample variance. So that's a sample variance. Sum of square deviations divided by degrees of freedom. Degrees of freedom is the size of your sample minus 1, and your sample standard deviation is just the square root of that. We take the square root of our sample variance. All right. So we're going to use that sample standard deviation. We're going to use the sample's variability to estimate our population's variability so that we can then estimate that unknown distribution of sample means. So we need to figure out this standard error. We need to figure out the standard deviation of the distribution of sample means. So instead of calculating the standard error, this one over here, which we calculated when we knew the population standard deviation, we're going to calculate the estimated standard error, the standard error of this estimated distribution of sample means. So the standard error before was calculated by taking the taking the standard deviation of the population and dividing by the square root of the size of the sample. That's what we learned last time. Estimated standard error is you take the standard deviation of the sample and you divide by the square root of the size of the sample. So literally that one substitution, not the population standard deviation, but now the sample standard deviation, that's the change. That's the difference in terms of how we're calculating this new distribution of sample means. All right, any questions on that so far? Okay, so now we have an estimated distribution of sample means because we're not using a known standard deviation of the population, we're using an estimated standard deviation for the population. So what this means is that when we determine our cutoff score, we're no longer using a z distribution, right? Because we're now estimating the z distribution. So we don't know what the z distribution is because we're estimating the z distribution at this point. What that means is that when we determine our cutoff sample score on the comparison, we cannot go to that unit normal distribution table anymore. We cannot go to that table filled with z-scores. So this distribution is no longer something that we have access to because, again, we did not know the population's standard deviation. However, that does not mean that we're not dealing with a distribution. That does not mean that we're not dealing with a distribution that's symmetrical and bell-shaped. Basically, the only thing that's changed is our distribution looks like this now, and it's not a z distribution, it's a t distribution. And the big difference between a z distribution and a t distribution is because a t distribution is using an estimate of variability, it tends to have more weight in the tails than the z distribution. So more of a t distribution is in the tails because the variability when you estimate things can go wider. So we end up with more possibilities or more sample means in the tails than we used to have for a z distribution. So that's the first difference between a t distribution and a z distribution. The other difference is that a t distribution, the shape of it changes as your sample size gets bigger. So for this t distribution, this is for 1 degree of freedom, i.e. a sample size of 2. If we go to a sample size of 3, this is what our t distribution looks like. If we go to a sample size of 4, so 3 degrees of freedom, that's what it looks like. Sample size of 5, 4 degrees of freedom, that's what it looks like. Sample size of 6, 5 degrees of freedom, that's what it looks like. Sample size of 11 with 10 degrees of freedom. Sample size of 21 with 20 degrees of freedom. So you can basically see that it does change its shape as the degrees of freedom increase. And also it just gets more and more like a z distribution as the degrees of freedom increase as well. So everything that you learned about the z distribution and how to work with the z distribution, carry that over to the t distribution. The biggest difference is that we are now taking into account degrees of freedom as well. And we have this new distribution, which means that we now have to flip to a new table of values. So much like the z distribution, statisticians have figured out everything we need to know about this t distribution, and they put that information into our t distribution table. So the big difference now is that instead of flipping to Appendix A1, you are going to flip to, I believe, Appendix A2 or B1. It's one of those two. Basically, it's the next table of distribution values, your t distribution. All right, so that was step 3. When we look for our cutoff scores, we have a new distribution, our t distribution table. Step 4, determine your sample score on the comparison distribution. So we still have a comparison distribution. We still have a sample. We need to find out, is that sample in the tails or is that sample in the body? And this is going to be so much like what we've done before that, again, it's just a slight change. It's that blink and you'll miss it change. So the T statistic, there's a new formula for calculating out the T statistic. That's what it looks like. If you remember the formula for calculating out your z-score, that's what it looks like. And basically the only difference is that instead of using the known standard deviation for your comparison distribution, we are now using the estimated standard deviation for the comparison distribution. But everything else is the same. Your sample mean is still your sample mean. The mean of your comparison distribution is still the mean of your comparison distribution. Basically, everything has remained the same. It's just that the standard deviation is that estimated standard deviation, that estimated standard error. So again, blink and you'll miss it. This is the T statistic formula. And we have it here written as standard deviation. You can also write it in terms of the variance divided by the size of the sample. But again, note that the numerator there, same exact idea. You take your sample mean, you subtract away from it your comparison distribution mean, which is also your population mean. But then when you divide it, make sure that you're dividing by that estimated standard deviation, that estimated standard error. And that is why that difference is the reason we can't use the Z distribution anymore. That's why we have to use the T distribution. All right. So as you can see, mostly the same kind of stuff, and things that are different are very similar. So a T distribution is very similar and works in much the same way as a Z distribution. So the situation we have right now, we have an unknown population where we have a hypothesized mean. That is, if the null hypothesis was true, that would be the mean that we would expect. We have an unknown standard deviation for our population. Because of this, we have a T distribution now of sample means from that unknown population, where the mean of our T distribution of sample means is the same as the mean of our population, but the standard deviation is the standard deviation of the sample divided by the square root of the size of the sample. And from that, we're going to do the exact same thing that we've always done. We're going to find out what is the probability that our sample mean could have come from this T distribution. We're going to draw our lines in the sand. If, when we calculate our means, our sample means T statistic, it's within the body of the T distribution, we're going to accept the null hypothesis, and we're going to say it's highly likely that our treated sample belongs to that distribution of sample means, which means that it still belongs to the population. However, if our treated sample mean is located in the tails, that means that it's highly unlikely that our sample came from this population, because look, it would only come from that population if it came from those tails. That means that it's highly unlikely to be a part of this population over here. That means that our treatment has fundamentally changed our sample. So if our treated sample ends up in the tails of our distribution, that means that it's not a part of this population anymore. It's very unlikely that it's a part of that population, and it's much more likely that it's a part of this treated population, this new population that we changed our sample into. All right. Any questions on that, the basic idea? All right, let's see it in action. So once again, going back to Harlow and his monkey study. This time, however, we're doing it the authentic way. This time, we don't know how long these monkeys are spending. We don't know anything about the population of monkeys. We don't know the standard deviation of the population of monkeys. All we know is that we have a sample of 9 monkeys, and we know how long they spent with a terror clock mother. So once again, just to set it up, just to remind you, in this classic study of infant attachment, Harlow placed infant monkeys in cages with 2 artificial surrogate mothers. One mother was made from bare wire mesh and contained a baby bottle from which the infant could feed. The other mother was made from soft terry cloth that did not provide any access to food. Harlow observed the infant monkeys and recorded how much time per day was spent with each mother. In a typical day, the infant spent a total of 18 hours clinging to one of the 2 mothers. So that is a very important number to remember. In a typical day, these monkeys had 18 hours to spend with either the terry cloth mother or the wire mesh mother. If there was no preference between the two, way better markers. If there was no preference between the two, and they spend 18 hours a day with those two mothers, then we would expect that they would split that in half and spend 9 hours, with the wire mesh mother and 9 hours with the terry cloth mother. So we don't know about the population of monkeys, how long they actually spend with the terry cloth mother, how long they actually spend with the wire mesh mother. But we do know that in this situation, they had 18 hours that they could spend with either of these two mothers. It was 18 hours where they had access to these mothers in the lab. And we then can hypothesize that if they did not prefer one mother over the other, on average, this population would spend 9 hours with the wire mesh mother, and this population would spend 9 hours with the terry cloth mother. So that we know, if our null hypothesis is true and there's no preference, they'll spend 9 hours with one mother and 9 hours with the other. So if there was no preference between the two, we would expect the time to be divided evenly with an average of 9 hours for each one of the mothers. However, the typical monkey spent 15 hours per day with the terry cloth mother, indicating a strong preference for the soft, cuddly mother. So suppose we had a sample of 9 infant monkeys, and they averaged 15.3 hours per day with a sum of squared deviations of 216 with the terry cloth mother. Is this result sufficient to conclude that the monkeys spent significantly more time with the softer mother than would be expected if there was no preference? Use a two-tailed test with an alpha of 0.05. So we know that our sample has spent 15.3 hours with the terry cloth mother, which means that either they belong to this population of monkeys that have no preference for either mother. This is the population of monkeys that have no preference for either mother. 9 hours is spent with the terry cloth mother. These monkeys over here, they spend very little time with the terry cloth mother. These are the monkeys that love the wire mesh mother. They're still part of this population, but they love that wire mesh mother. These monkeys over here, these are the terry cloth loving mother monkeys over here. Mother loving terry cloth monkeys. Where's Samuel L. Jackson when you need him? These are the ones that love the terry cloth mother. Still part of this population, but they love the terry cloth mother. Our sample of monkeys that spend 15.3 hours with the terry cloth mother, they either, really don't know how to spell today. They either do not belong to this population. They either do not come from the population that has no preference for mothers, or we got unlucky enough that we just chose these terry cloth loving monkeys. We got unlucky enough that we only chose monkeys randomly from this area of the population. So what we're going to see is how unlikely is it that we only chose those monkeys. And if the likelihood is low, we're going to say that these samples belong to a different population that loves the terry cloth. But if the probability was high, then we're going to say that they do belong to these monkeys that have no preference for one or the other mother. So let's take a look at what that situation is. We're going to do a two-tailed test with an alpha of 0.05. So some of this is going to be a review because, as I mentioned before, parts of the hypothesis test does not change. So restate the question as a research hypothesis and a null hypothesis about the population. We're asking the same question we asked the previous times we looked at this. Is there a preference for the terry cloth mother or for the wire mesh mother? basically, do you spend more than 9 hours with one of those two mothers? The research hypothesis is that there is a preference for one of the two mothers. What that means is that the time that they spent with the terry cloth mother does not equal the time that they spend with the wire mesh mother, does not equal 9 hours. So the terry cloth mother does not equal the wire mesh time spent with the wire mesh mother. That means that they belong to this population over here, to that treated population that prefers one of the mothers. The null hypothesis, on the other hand, is that there is no preference for either mother. That says that they are going to spend the same time with the terry cloth mother that they do with the wire mesh mother. And then if they can only spend 18 hours in total with the two mothers, if that's the case, they're spending 9 hours with each mother. Because 9 hours here, 9 hours there, that's the only way to get those two equal and have them add up to 18. So if this is the case and they have no preference, they belong to that hypothesized population, the population where they're spending 9 hours with the terry cloth mother. All right. Step 2, the new stuff. Determine the characteristics of the comparison distribution. All right, so the mean of the distribution of sample means, the mean of your comparison distribution is the same as your hypothesized population, so that stays the same, and in this case, it's 9 hours. So the mean of our distribution of sample means is 9 hours. That's what would occur if there was no preference between the two mothers. They would spend 9 hours with the terry cloth mother. So we have the mean. We also need the standard deviation. So for the standard deviation, we don't have access to the population, so we need to calculate first the sample variance. So we were given the sum of squared deviations. We were given the size of our sample. We're going to go way back to, I believe, the second week of this course. And we're going to remember that the sample variance equals the sum of squared deviations divided by the size of your sample number minus 1. That's the sum of squared deviations divided by the degrees of freedom. Question told us that the sum of squared deviations was 216. The size of our sample was 9. So we have 216 divided by 9 minus 1. And we get a sample variance of 27. Once we get the sample variance, we can then compute the estimated standard error. So the estimated standard error, you take your sample variance, it's the square root of the sample variance divided by the size of your sample. That is mathematically equivalent. That's the way that your the textbooks like to do it. That is mathematically equivalent to the standard deviation of the sample divided by the square root of the size of your sample, so don't get thrown off by that. So we have the square root of 27, which was our sample variance, divided by 9, which is the size of our sample. And we get the square root of 3, or an estimated standard error of 1.73. So now we have our comparison distribution. It has a mean of 9, and it has a standard deviation of 1.73. We now know that about our comparison distribution. All right, so we have the characteristics of the comparison distribution. Next thing we got to do, we got to set a cutoff sample score or a critical value, aka we got to draw those lines in the sand to see whether or not our sample crosses those lines. So that's step 3 right now, the target against which we're going to compare the results of our study. This is where we have to go to the table and make sure that you're going to the right table. So make sure that now that we're doing t-tests, now that we're using that t-distribution, make sure you go to table, and it was A2, and look for the t-distribution cutoff scores. So for the t-distribution, it's set up a little bit differently, but it's the same basic idea. So for our t-distribution, we have a sample size of 9. We have a two-tailed test with an alpha of 0.05. So all of that information is what you got to remember and what you got to bring to your table. So once again, we're going two-tailed, because that's what the question wants us to do. We have an alpha of 0.05, and we have a sample size of 9, which means that we have a degrees freedom of 9 minus 1 equals 8. So you need this information going into your table because of the nature of a t-distribution. So we have all that information. We get that from our question and figure out the degrees of freedom. It's the size of your sample minus 1. And then we just start narrowing down our cutoff scores from the t-distribution. So it's almost kind of like a homing missile where you're just kind of like, getting in, zoning in on your target. So the first thing we can do is decide whether we want this half of the table for one-tailed tests or this half of the table for two-tailed tests. So we look at our question and it said do a two-tailed test. So we're going to be looking at that side of the table right there. Next thing we need to do is we need to figure out which row are we looking in, so we know we're in this half of the table. Next thing we do is we look at which row we're in. The row depends upon the degrees of freedom. We have 8 degrees of freedom. We got 9 monkeys in the sample. 9 minus 1 is 8. So we zone in on that row over there. So now we know that we're looking at one of these 3 numbers over here. And then the last thing we need to do is we need to figure out which alpha level are we working with. Is it 0.10? Is it 0.05? Is it 0.01? Question says it's 0.05. We zone in on that, and we get our cutoff score right there. So you're going to need those 3 pieces of information. You're going to need one-tailed or two-tailed. You're going to need your degrees of freedom. Make sure you do not use the size of your sample. Make sure to take that one away. Remember the potato salad. And then your alpha level, and those 3 pieces of information will zone you in to that cutoff score. So once again, you're using a cutoff score. Once again, you're using a distribution, this time the t-distribution. All right. So we have our cutoff scores. This is the way it's typically reported. So t-distributions, because they change with this with the degrees of freedom, you report the degrees of freedom when you use a t-distribution. So we have a t-distribution with 8 degrees of freedom, gives us these cutoff scores of plus 2.306 and minus 2.306. So once again, we have, let's get rid of this carry clock 11 population. We have our comparison distribution, and it has a t-distribution mean of 0, and we have a cutoff score here at minus 2.306, giving us one tail, and we had a cutoff score over here at positive 2.306, giving us this second tail. So much like our previous z distribution. Last thing we got to do, we got to determine our sample score on this comparison distribution. So where are our 9 monkeys on this comparison distribution? So in order to do that, because this is a unit normal, you can think of it as a unit normal t-distribution, we have to take our sample mean and transform it into a t-score, and we do that using our formula for the t-score. So again, the formula for a t-score, very much like the formula for a z-score, we have our sample mean. We get that from the question. Our monkeys spent 15.3 hours with a terry cloth mother. We have our comparison distribution, has a mean of 9, has a standard deviation of 1.73. We use our T statistic formula, which looks almost exactly like a Z statistic formula. We plug in the values, 15.3 for the mean, minus 9, all of that divided by 1.73, and we get a t-score of 3.64. So, if this is 0, the mean of a t-distribution, And this is the cutoff at 2.306. That's 0, that's 2.306. There's our 9 monkeys. Right about there is our sample mean. It's crossed the line. It's gone over into the tails. That's where our monkeys are located. So now when we figured out where they are on the comparison distribution, last thing we do is decide whether or not we're going to reject the null hypothesis. This has not changed. This is literally the same 2 slides with the word t-score substituted in for z-score. So if our sample t-score is beyond the cutoff score, if it's crossed that line into the tails, which it has, we accept the research hypothesis and we reject the null hypothesis. They really liked accepting the research hypothesis. All right, so we accept the research hypothesis and we reject the null hypothesis. That's exactly what happened. That's what we're going to do. If, on the other hand, our sample stayed within the body of the t distribution here, if it did not cross into the cutoff scores, then we would accept the null hypothesis and we would reject the research hypothesis. However, our monkeys crossed over into the tails, which means that it is very, very, very unlikely that they came from the population that has no preference for the mothers. It would have to have been all extreme terry cloth loving monkeys from this population in our sample. That's highly unlikely, so we accept the research hypothesis, we reject the null hypothesis, and we conclude that monkeys prefer the terry cloth mother, that the actual population of monkeys that our sample is from have a preference for that terry cloth mother. And from that, Harlow, after doing an analysis just like that one, came to the conclusion that this is one of the reasons why infant attachment is so important, and this is one of the reasons why today's parents do not just provide food, clothing, and shelter for their children and then call it a day, because that's the wire mesh mother, and for psychological development, you need the affection and the caresses and the warmth. All right, any final questions on that T statistic? Okay, so you can see that there was a lot of steps, there was a lot of formulas, there was a lot of kind of figuring things out. This is going to be the last of those days where we're going to be doing that. So just one last time so you can practice it once more, so you get one more peek behind the curtain. We have our homework assignment, assignment number 10, chapter 8, part 1. So this is going to be just on the single sample t-test. So this is due October 29th by midnight. I'm still going to be updating the previous pre-test based on your mastery points. I'll be doing that sometime at the end of this week. But also plan on accessing your study plan. Get those 100% on your pre-test points if you've missed any of those points. And that is all that I wanted to do today. So this was our first example of an actual, authentic, you will run into this situation in your psychology career hypothesis test. Next time we meet, we're going to be looking at the same idea of a t-test, this time with dependent means, and we're going to be introducing SPSS. So be sure to plan on attending next time. If you absolutely cannot, stay up to date with the videos posted to my YouTube channel of the lectures. But that is all that I wanted to cover for today. All right, so if you want to call it an early end to the week, feel free. If you want to stick around for the next, looks like 20 minutes, maybe start on your homework or talk to me about anything else, feel free as well. Other than that, we are done for today.